So my name is Seun Lanlege, and I know it says principal, protocol, whatever. Basically, protocol lead at Composable. And as you probably don't know, Composable is trying to build cross-chain applications. It's kind of in the name. We're trying to compose multiple applications across different chains and present that to users in a unified manner. Well, in order to do this, we do need bridges. And after sort of taking a survey of all the varieties of bridging architectures, we've come to the conclusion that trustless bridges are, well, the best kinds of bridges. So this talk will just basically walk you through why, trustless bridges, how trustless bridges, give you a small demo of what we've built so far, and we can just do a little bit of Q&A. So the first thing is I want to note to you is why do we need trustless bridges? Let's take a step back. We've tried to build decentralized applications, right? That's what we're building. We're not really building centralized application. We're not building centralized infrastructure. We want to build decentralized applications. And we can host these decentralized applications on a single L1. Right. But that has proven to be unscalable. And the reason is it's like basic physics, right? You have a bounded network, and then you're trying to host an unbounded number of applications, which will also have an unbounded number of users, and they all now start to compete for block space. That doesn't turn out well. And we've seen this in Ethereum, and a lot of blockchains acknowledge this limitation. Well, enter application-specific blockchains. And this was introduced in the Vision for a Heterogeneous Multi-Chain Future by Gavin Wood et al. And the idea is simple. What if instead of having multiple decentralized applications on a single blockchain, instead each application is hosted on its own blockchain? Now, what does that give us? Well, that gives us lighter blockchains. Essentially, you don't have state bloat. Each blockchain is responsible for its own state, maintaining its own state, which of course, leads to lighter blockchains. It leads to cheaper fees because, you don't have competition against multiple applications and users, and so you can actually have really, really stable fees for your application. And of course, it's highly scalable. Now, the problem with the generalized L1 is that it has to make decisions for all the applications. Whereas if you have an application-specific blockchain, you can design it such that you can squeeze out as much performance from this application-specific blockchain. But now, if every application is in its own blockchain, right, so how do you compose application-specific blockchains? Well, you do need cross-chain bridges to do this, right? And so we now see that cross-chain bridges are critical to the next logical step of the blockchain infrastructure. But then cross-chain bridges are hard, right? We've seen the bridge hacks, we've seen everything. Everyone at this point is kind of wary of bridges at this point. But I'm here to tell you that it's not justified. Cross-chain bridges are possible. In fact, lots of ecosystems already have trustless bridges. Cosmos has trustless bridges. Parachains talk to each other via trustless bridges. But, what we need are cross-ecosystem bridges, cross-consensus bridges, so that, multiple ecosystems can talk to each other. And so we've seen that light client-based bridges are, the only provably secure cross-chain bridging architecture. You can try to have an oracle, a third-party oracle in between two blockchains that acts as this, oracle for the states of the counterparty blockchains, but that introduces a new trust assumption on the system, which you probably don't want. Now, okay, we agree that light client protocols are secure. But then light client protocols come in two flavors. You have the fully trustless kind, and you have the trust minimized kind. Now, it's important to note that this, if you have a light client-based bridge, the light client security comes from the light client protocol of the counterparty chain. The counterparty chain decides if its light client protocol is fully trustless or trust minimized. And I'll give you examples of this. We come to the fact that light clients themselves also have vulnerabilities. These vulnerabilities are not new. They are as old as the first light client protocol, which is the Bitcoin SPV protocol. And we'll also look into the vulnerabilities themselves. So let's look at light client protocols. I mean, you already know this. I feel like I don't have to tell you what a light client protocol is. But then we can look at the specific ingredients that enable bridges to exist. And essentially, you have finality proofs. Usually, this will be signatures of the authority set signing what they think is the latest block. And yeah, that's basically some cryptographic proof that guarantees that some blocks are final and cannot be reverted. And you have state proofs, which would be Merkle proofs of the data that exists within the blockchain state. And then you have this extra thing called ancestry proofs, which is an optimization on light client protocols that allows you to prove ancestor blocks just by knowing the latest block. You don't have to be aware of every header in the chain. And of course, that's what that means. So I'll just run through a brief overview of blocks because like all of this is going to be necessary as we move on. So you have a block, it has some header, it has some transactions, and the header, you can think of it like as a metadata of the block. And the header itself contains a consensus proof, the state root relevant to state proofs. It contains the transaction root, but that's useless to us in this context. And that's about it, actually. And now we have the state tree. I'm sure most of you have seen this picture before. A state tree basically describes the state of a blockchain. And we have the state root, which represents a commitment to that state. So, trustless light client protocols, what does that even mean? Well, a trustless light client protocol describes the exact same protocol that full nodes on the network will follow. So a trustless light client protocol means that a light client and a full node will never diverge. They essentially share the same security guarantees. And of course, algorithms with this feature are Grandpa, Beefy, Tendermint, Near. Now, I want you to like notice a pattern here. Protocols that have fully trustless light client support are mostly application-specific blockchain platforms. So Near, Tendermint, Cosmos, they all follow the application-specific blockchain paradigm. Trust-minimized light client protocols. So this is a protocol where it's very possible that the light client and the full node will diverge because, well, they have a much, less secure trust assumption. And so, yeah, basically a trust-minimized light client protocol introduces a new, weaker trust assumption than full nodes. And usually that's just validator subsampling. You're subsampling the validator sets and telling them to produce proofs for light clients. And, the Ethereum protocol is guilty of this. And you will see that they don't really subscribe to the application-specific blockchain paradigm, so they don't really want to have a fully trustless light client protocol. So, based on our knowledge of light client protocols, we can start to design a very naive bridging protocol. Well, we know that we want to be able to commit some outgoing messages to a blockchain in the originating chain's state tree, and that allows us to use state proofs to prove that that message does exist. And now we can also then verify the finality proofs of this chain so that we can be sure that the state will never be reverted essentially and it's final, and we can trust that because we have proofs of this. So we can verify the state proofs and then we can then execute these messages that are incoming and vice versa. So this happens on both chains. And I'm just going to show you a small half of the picture. So you have a blockchain, it has a light client running on it, it stores the previous headers. The relayer, which is an off-chain process, observes new blocks on the counterparty chain and it submits these new blocks, as well as the state proofs for the messages, as well as the finality proofs for these headers. And that's kind of what that's supposed to signify. So we now understand what a bridge kind of does underneath. But what are the vulnerabilities of this bridge? What is the vulnerability of light clients and, of course, by extension, light client-based bridges? Well, 51% attacks. Kind of standard. We also have something called a long-range attack, and this is actually a vulnerability of proof-of-stake-based systems. Like, even full nodes are vulnerable to this. And so, by extension, light clients are vulnerable as well. Well, we have an eclipse attack. Also, full nodes are vulnerable to this, depending on how you structure your blockchain protocol. And there are two kinds of eclipse attacks. We have the equivocation eclipse attack, where validators are going to sign two different conflicting headers and claim that they're final. And this is basically called an equivocation. And then you have a more devastating variety, which is called the data withholding attack. So they will sign a header, but not broadcast the blocks or the transactions behind this header. And so they've essentially stalled the blockchain for the purpose of fooling light clients, whether they're off-chain or on-chain. And so this is what a 51% attack looks like. They basically, you have a supermajority set that finalizes two chains. And then, actually, 51% attacks may not necessarily be an attack directly on the bridge. Maybe someone's trying to attack your blockchain protocol, but now, by extension, your bridge is vulnerable to this attack and is vulnerable to double spends. We move to the long-range attack, which is basically you have malicious authorities that are on stake at some block, and you have a light client that is unaware of new blocks. So they're still stuck at, this light client is still stuck at block 100, and they're on stake at this block, and they go back in time so that they can create this fake chain and finalize this fake chain. And then they can update the light client on-chain, essentially fooling this light client to believe that some state is real when it in fact is not real. Like I said, not only applies to light clients, actually applies to full nodes as well. And this is kind of what brought about if you follow the Ethereum community, they have this idea of a weak subjectivity period, in which they checkpoint some blocks so that the network agrees that these blocks are final, and you really shouldn't have a conflicting view after this point in the network. And then we have the Eclipse attack, where essentially you have some on-chain light clients, and I'm just like off-chain light clients are also vulnerable to this, but I'm only going to talk about the on-chain light clients in this case. So you have an on-chain light client that is aware of block A, and you have a validator set that thinks to themselves, well, I could technically sign a fork of the chain, submit that to the on-chain light client, and the light client will believe me. And now this light client has been fooled into believing a chain that is not real. In this attack, they could essentially mint an unlimited amount of tokens. And of course, you have the Eclipse attack of the data withholding variety, where essentially there is no equivocation. There is no two final chains. There is only one final chain, but this chain, the block isn't valid. So these blocks actually violate the state transition function of the chain. And that is why they do not gossip the full block data, because they know that full nodes will reject this. But now, light clients do not check the full block data. And now, of course, they're vulnerable to this attack, because now they've stalled finality and they're waiting for light clients to essentially accept this block. Now, this is a major light client vulnerability that actually spurred the paper Fraud and Data Availability Proofs by Vitalik Mustafa et al., where they describe that the only way to solve this is to have a data availability layer which blocks get committed to, and light clients sample that this data is available, that the full block data is available, so that they can be sure that, well, if the data is available, that means someone can check the data and it can be reverted if it's not valid. So if you go back to our naive bridging protocol, we essentially have sophisticated cryptography, but we didn't actually take cognizance of game theory. We did not assume, rather we are assuming that our validators are not going to be Byzantine. But the truth is, blockchain protocols themselves do not make that assumption, right? That's why you have slashing protocols for when they misbehave. So why shouldn't bridges also make that same assumption that your validators can be Byzantine? So in order to make our bridges Byzantine fault tolerant, it is necessary to reintroduce game theory. And we do so by introducing a challenge period in between when you submit headers and finality proof for these headers, and when you can then submit the state proofs of these cross-chain messages. And what that allows us to do is to introduce a third party in the bridging system that will check if these headers are actually valid, or if there's a data available for these headers, or if it's a fork. And that would allow them to submit the competing heights for these headers and then freeze the bridge. So for the long fork attack, we basically have to now make sure that the light clients are aware of time. The problem with the long fork attack is that the light clients are not aware of time. They don't know that the time it takes for the counterparty chains to unstake has passed, and we can no longer trust anything coming from the counterparty chain. And also, like I said, we have this third party called Fisherman, stolen from the paper by Gav. to basically check that light clients are being updated with the correct headers. And also, it's clear that for data withholding attacks, the only thing that we can do is to freeze the light client once we detect that the blockchain has stalled finality. Really, there's nothing we can do. There's no competing header to submit an equivocation for. So there just needs to be a fail-safe, an emergency shutdown button that says, oh, well, the bridge has been compromised, shut everything down. And so this is basically a visualization of what this new protocol will look like with this challenge period. So this is an Eclipse attack. This is the canonical chain. The light client has been fooled into accepting the forked chain, but it doesn't accept the state proofs for the messages immediately. It's going to wait for a bit to see if they get challenged. And now you have a honest relayer who thinks, well, this is the correct chain. They send that correct chain to the light client, and the light client can see that, well, there are now 2 chains that are valid, and it can freeze all bridging operations immediately. Now, this allows us to prevent any loss of funds that may come from a Byzantine attack. So this is also a visualization with the fishermen. So the fishermen, they're watching the light client updates. So I should note that this last slide assumes the existence of a single honest relayer. In the case where there's no honest relayer, we rely on fishermen who will essentially watch the light clients, the headers that get updated to the light clients, and see, well, this is not the right chain. And then they will basically take these headers off chain and then submit them back to the chain where they come from so that the offending validators can be slashed. And they can also freeze the light client and let the light client know that, well, this chain is bad. So, given everything we know now, we can now build what I would like to call a truly trustless bridging protocol. And it's trustless because it doesn't believe that the authority sets cannot be Byzantine. It actually doesn't even trust the authority set at all. So yeah, like I said, it's Byzantine fault tolerance. It's also based on the IBC protocol. We use the IBC protocol for messaging. The IBC protocol is generic enough that you can put in any light client implementation in there, and you get a really nice messaging protocol that supports ordered channels, unordered channels, message timeouts, all that fun stuff. We also have multiple light client implementations for various L1s. We've implemented a beefy light client, a grandpa light client as well. We're currently working on a near light client and other blockchains as they come. We've also built the first chain agnostic IBC relayer. IBC was originally built for the Cosmos ecosystem. And so they didn't really have a lot of chain agnostic infrastructure, and we had to basically step in and extend the IBC protocol to make it chain agnostic, and then build the first chain agnostic IBC relayer. And of course, we have the Fisherman protocol implementation for reporting equivocations and collecting slashing rewards. And of course, we have the Sentry bots, which will basically watch for data withholding attacks and immediately push that emergency shutdown function. So I was going to show a quick demo. Just let me. So tiny. Yeah, so it's so tiny on my screen, I can barely see anything. I don't think this is going to work. You know what? I will put a video up. We actually already have a demo, so I'll put the video up later, and you guys can go check that out. So we'll just skip the demo for now. Yeah, fully trustless, right? So I was going to show you cross-chain transfers and stuff, but yeah, it's not a great place. But you can go check out our repo. It's at this link. We have implementations for everything that I've described. And so just to quickly show you our roadmap, we currently have a parachain to parachain bridge completed. So this is without XCM. This is using IBC and all this light client and fisherman stuff I've described. It's an implementation of IBC, so you have to have Palette IBC. We have the ICS-10 grandpa light clients and the hyperspace parachain relayer. We plan to upgrade to Beefy once Beefy goes live with Kusama and Polkadot. Like I said, we have a parachain to near bridge ongoing, and that would require, well, a near light client as well as near support for our relayer. And of course, IBC implementation for the near contract environment. Also, we have a bridge to Cosmos ongoing, and that just requires the relayer support. There's already a light client implementation for Cosmos in Rust. And right now we also have Ethereum Bridge ongoing. This just requires the SIG committee, light clients, and hyperspace Ethereum relay support. Of course, there's also a need for Solidity IBC, which is basically IBC implementation in Solidity. There's already an implementation of this made by the really smart people at DataChain. And what is the future of trustless bridges? Well, I would like to say that the next logical step is that we start to introduce what are called ultra-light clients. And this word was actually introduced by the Plumo team. Plumo is the first ultra-light clients where they basically use a ZK circuit to prove the state transition, sorry, not state transition, the epoch transition function for CeLO. So ultralight clients are essentially using ZK circuits to prove the finality predicates for blockchains. And you get the benefits of having a succinct proof that's independent of the size of the validator set to verify the finality of blockchains. And also, vertical trees are a new kind of tree structure that allows for succinct proofs for state trees. So what this unlocks is basically higher bandwidth messaging. We're no longer constrained by the O log n complexity of Merkle trees. So I have my references, and do follow me on Twitter and Medium. I have articles on trustless bridging, and I do post about the latest in blockchain protocols. Thank you very much. Maybe questions if you guys have any.
Talking about the Eclipse attack, right? If there is a proof that 66% said to fork, then where are you going back to say is because 66% of validators are compromised, right?
For sure.
Then you can't go back and check it.
Go back how?
That's exactly like you said. You said you will go back, no? And then verify. Like the fisherman, for example, is reporting double thing. What is next step? Like if 66% of validators are compromised, what is next then?
Right. So here. So they're not compromised in the correct sense, right? So the problem with the Eclipse attack is that there's no penalties for lying to an on-chain light client that is outside of your blockchain. You can't get slashed for that. It's impossible. Unless someone were to tell on you.
I see. So they sign honestly on chain, but the message they send is a lie. Okay.
Yes.
And then what is the honest relayer? That doesn't exist, right? Because it's trustless.
So this is a game theoretical assumption. We're saying that sure, there might be a malicious set submitting the fake chain, but there's also going to be an honest relayer at some point also doing the correct thing. And so while this submits the fork chain, the honest relayer will submit the canonical chain, and the light client will observe that these two chains are final, but they describe entirely different states, and so they can freeze the bridge.
So why does such a player exist? Like, what is their intention to be existing?
So, I mean, I would assume that we have a bridge and we have our own relayers, right? But then anyone can be a relayer, including this Byzantine set. So they will lie to the light client, right? But then our relayer wouldn't lie to the light client. They would present the canonical chain.
Because you trust your relayer. But it's not trustless, but it's okay. The last thing is the fishermen. Why do they? So that was the problem we had with Polkadot. The fishermen, they don't really get money because their work is to make sure people get a slash, and because people know they exist, and so they don't lie, and then they will never make money. So why do you run your fisherman for a year while you pay for the server and you get zero reward?
Well, so that's the thing. The fisherman is not really to report. It's a disincentivization mechanism. It's like you said, if we run fishermen, no one will attack our light clients. And so hence, yeah, sure, we will never get money. But it's there to prevent people from doing that in the first place.
But nobody runs them.
We will run them personally.
Okay.
We will run our own fisherman nodes by default. And anyone in the community can also run their own fisherman nodes.
There's a lot of trust is okay, but people should trust your company, basically. because you say I'm running fisherman, I have an honest relayer, but it's okay. It's just it's not completely trustless, right?
I totally get your point, but anyone can run a relayer and anyone can run a fisherman node.
Yeah, sure.
So it's still decentralized and trustless. It's not permissioned.
It's true.
Right. So you fish out like so. First, really great talk. Thanks. So once you report that there's been equivocation, then the slashing happens on the target chain or the source chain? On the target chain.
Source chain.
On the source chain.
Yeah.
Okay.
You can think of them as the goody two shoes reporting back. To
Okay.
the source chain.
So if that chain goes like, well, but the ones who are in control of the source chain are those validators who have equivocated.
Yes, for sure.
So isn't there a stronger argument to be made to do the slashing on the target chain and have them deposit funds there instead?
Well, they are staked on the source chain.
But if you stake them as well on the target chain where if, like, say you're bridging to, I don't know, Ethereum or something, and if you're a validator elsewhere and you're building a light client to that side, then you also require them to stake some ETH.
I think that it's possible, but it is complicating the protocol quite a bit.
But in this case, like, yeah, okay, it does complicate it quite a bit. I'm just thinking that at that stage they're in control of the source chain, so they're also the ones in charge of enforcing the slashing.
So what I see will happen is the same thing that will happen if they did fork the source chain. Like, it's not an attack on the bridge, they were trying to attack the chain. The chain would have to halt so that we can resolve what's happened. So the same thing happens, right? When we see the equivocation and we try to report it, we can then elevate it to governance that your validator set is completely Byzantine. So we should fork this chain and rotate them out of the authority set.
Yeah.
Okay, I'll think of this some more and then maybe get back to you later. Yeah. Cool, thanks.
You're welcome. Some questions?
So I was wondering, how does like the light client initially synchronize to get the latest finalized block? Do you use like some snapshot from which you start syncing, or?
Like the initial state for the light client? I mean, it's subjectively chosen. So yeah, you do have to trust that we will choose the correct block, but like that's going to be public for anyone to see.
Mm-hmm. So you start with like a snapshot
Yeah.
to get the initial sync going.
Yeah, for sure.
Okay.
Hey, hi there. Yeah, so I'm interested in your parachain to Ethereum bridge, and I was wondering, do you like just check a subset of validator signatures, and if so, how do you use like random? How do you use Ethereum to use randomness to select that random subset? Or generally, I'm just curious about your high-level architecture for the.
Right. So we are not the ones who do that subsampling. The Ethereum Sync Committee already describes a protocol for subsampling, and like it's part of the protocol that this subsample of the validator set are producing light client proofs.
I'm talking more about Beefy, basically.
For Beefy, we validate the full 2/3 plus 1 signature set. I mean, yes, it's expensive, but like it's a good price to pay for trustlessness.
But that must mean your latency is like 4 hours or something. That's a lot of data to process.
Yes, so yes, we trade security for latency, which I think is a good deal.
Sure, yeah, sure. Okay, cool, yeah, cool.
Any questions?
Can I also ask a question? I would ask one question. To make a trustless bridge, I think both chain need to implement light client node, right?
Yes, for sure.
And you say also you're thinking to have bridge with an Ethereum, and how do you try to because to making a trustless bridge with Ethereum chain, Ethereum community also need to implement, I think, light current node, right, in Ethereum. How do you want to make it possible?
So the Ethereum protocol already has a light client protocol.
I
Yes.
see. Okay.
So we don't have to implement it for them.
Oh, okay. Thank you.
Maybe to tag on to Vincent's question, what kind of latency does this challenge period induce?
So we're thinking an hour, and that should give us enough time or give the fishermen enough time to submit any challenges that may exist.
Okay.
I would also note that I was speaking to Alistair earlier today, and he talked about how challenge periods can essentially be censored. So someone could attack the bridge with this fork chain, and then buy up all of the block space for the challenge period. The only way to mitigate this is to make that challenge period expensive enough that it's unrealistic for a long, like if it's an hour, it's unreasonable that you can buy up all the block space for an hour.
Yeah, or to have specially reserved block space for challenges, but
True, but then, for instance, Flashbots is open for anyone, so anyone could submit this transaction via the private mempool to the validators.
What was the 4 hours? I didn't understand. Why does it take 4 hours to update the bridge?
1 hour for the challenge period.
Oh, okay, so you're waiting for after.
Yes.
Okay.
I think in the BB protocol, you have to check 2/3 or more validated signatures. So that's different from the challenge period.
So the challenge period is essentially a time delay in between when you submit this 2/3 plus 1 signatures and when you can submit the associated state proofs for messages with that header. So we assert that there are no forks, there's no eclipse attacks, there's no data withholding attacks within that period before you can now start to send over the tokens that were bridged by that header. All right. Thank you all for your time.